I have a couple of announcements. One of the announcements is to make sure that you read. Make sure you read the pre-lab. Of course, you need to do the pre-lab, but make sure you read through the lab carefully, like all the procedures. There's a lot of equipment, new things going on there, and it's preparation for this lab and the following lab. So please do that. And then the other thing that came up, which was a complete surprise to me, was that Sapling was going to charge $23.99 or something like this. Yeah. So that was a surprise to me. No one had told me ahead of time about that, or I would have talked about it with you before the course started, or I would have weighed the possibility of whether Sapling is actually useful for the course for $23.99. No one had told me about the charge. And to mitigate this problem, at least for the time being, we're no longer going to do Sapling. That doesn't mean we're not going to do the pre-lab. The pre-lab is required. Okay? Please don't come to lab unprepared, because all the pre-lab materials. This is really important, guys. All the pre-lab materials are at the beginning of the lab manual. So, please fill out those materials. And many of the questions on Sapling weren't helping because they're just saying, did you do this short answer in your pre-lab? Well, that's because Sapling doesn't do short answer. All right? And so I'm a little bit concerned about some of the limitations of Sapling at this point and how it fits in with the lab course. It fits in probably well with the general chemistry lecture course, but maybe not as well with the lab course. So we don't know what we need to do, and people that had assigned Sapling in the past or designed Sapling are going to talk with Sapling about this belated charge. And I thought it was completely disruptive to my course. So I'm not happy about it, and I'm on your side, but I do, I want to let you know that we're dealing with it. All right. So don't pay the fee. Don't worry about the Sapling right now. I'm sorry if you did pay the fee. I'm really sorry. It was a complete surprise. He wasn't supposed to do that for a week, and then he just did it right away. Just complete, All right. So we're going to talk about acid-base indicators, and drawn here already is just to save me a little bit of time is deprotonated methyl orange. Can you guys all be settle down? I know this is exciting with the Sapling charge and all. I know it's a major bit of gossip and controversy in my lowly course. Let's see. So this is deprotonated methyl orange, and so that would mean if we were to add a proton to it, and it's written in the dissociation direction, that we create the protonated form. This is an indicator that I'm not going to write out the exact structure here to save a little time, but this indicator is a way of sensing protons or pH changes. It protonates here on these simple nitrogens. And this is not the only possible resonance structure for protonated methyl orange. I'm not going to draw all possible resonance structures. That's the subject of an organic chemistry course that you'll take later when you learn about all these resonance structures. So you might go on the internet and say, Professor Krantz's drawing is wrong. Well, there's quite a few drawings for this, trust me. You can come to my office hour and we'll draw this out for you if you'd like to see that. But that's not really what we're here to learn. And the idea is that methyl orange takes on a proton at these positions, and that the affinity for that proton, the pKa, as we talked about in the previous lecture, is around 5. It's technically like 4 point something, 4.5, but to keep things simple and so I can have a nice little diagram like this of these beakers with even number, or rounded numbers, integers for the pHs, I just called it pKa 5. So don't call me out on that either. But this is a protonated methyl orange. This is a protonated methyl orange, and we like to refer to this as H-end. So we can write out this expression for H-end can dissociate to end plus a proton. Okay, and like I said, its Ka is equal to 10 to the minus pKa, so that's going to be 10 to the minus 5. Okay. All right. So if we took this indicator and put it in, I don't know, around micromolar concentrations, a little bit will go a long way. Then you'll see this range of colors as you change the pH. Okay. So on one extreme, deprotonated methyl orange is yellow, and on the other extreme, I call it red, but that's really dark orange. Okay. Whatever you like to call it, deep orange. I got in trouble last lecture because they're like, isn't methyl orange orange? And I'm like, well, that's the color. You have to use your artistic license there, whatever you like to call it. I don't really have an orange. You want me to make an orange just for fun? Okay. Bam. All right. Now I want my red back because I don't like orange. Okay. Obviously, I'm biased. I like to call that orange red. So as you change the pH of this beaker of methyl orange, when you're on one extreme at pH, you're going to favor the deprotonated state because you're way, way, way above the pKa, pH 8, right? So it's going to be completely yellow. And then as you come closer and closer to pH 5, or around the pKa, then you'll suddenly see a little of that dark orange color creep in to your beaker. Okay. And then eventually right at the pKa, remember, you're going to have a perfect balance, a 50% mixture of deep orange and yellow. And deep orange plus yellow makes normal orange, okay? Like orange juice orange, maybe. And then as you go past that point, okay, you're no longer going to have very much yellow deprotonated species in that beaker, and it'll become, bright, deep orange, methyl orange, okay? So that's approximately what it looks like. This is some, a Google Doc image. I'm not sure how faithful it is to the true colors, or it might depend on the camera that was used. And it also has to, some people are colorblind. They don't even see red very well. It'll look kind of brownish to them. Yes, that's a colorblind image there in black and white. But, different people see things differently. So what you do is you run a standard series like this, and you'll have an idea what your indicator is going to do. But the key point is that no indicator dye appears this color. No individual molecule is this color. Molecules of methyl orange are either, yellow or deep orange, okay? And yellow being that color or deep orange being that color. And when you see that medium orange color, that's just a mixture, okay? So that's the key. Now that doesn't mean that's the case for all dyes that sense pH. And so here's a bunch of them on the next page. So here's a big table of many different acid-base indicators that cover different pH sensitivity ranges. You can find these tables all over the place. There should be one in your lab manual, I imagine, or you can find them in your chemistry textbook. And there's one dye on here that's kind of interesting that the student pointed out last lecture, which actually violates what I just said, thymol blue. And you can see that thymol blue can actually be 3 colors, but that's because it has 2 titratable protons. One titratable proton is very, very acidic. It's down there in the pH range of about 1.2 to 2.8. And when that guy titrates, the dye goes from red when it's protonated to orange when it's deprotonated. But then it has another proton on it, and that gives us this name thymol blue. Because you're like, why would a dye be called thymol blue if it goes red to yellow? Doesn't make any sense. But it turns out it has 2 protons. So if you have 2 protons and those protonation states change the color of the dye, then you have this magic indicator like this guy. And he changes again in the pH range of 8 to 9 from yellow then to blue, and then it can be justified being called thymol blue. That's a weird case. They're not all like that. Generally, they just have one titratable group on them, and the color is pretty much limited to that one color change. So how do you get all these dyes with different pH ranges of sensitivity? Does anybody know what's the key difference in all these different dyes? It's a pretty straightforward question. Who knows? Somebody? No? Why do they have different pH ranges of sensitivity? Did I hear it right? Someone say it louder? Exactly. So what determines a range? Excellent answer. Yes, they have unique pKa's, okay? pKa values, okay? And so if you have unique pKa's, then you get a unique pH range. So the next question is this, and it is going to require a little bit of graphing. But why is it a range? Because a pKa is a discrete value. Okay, so why am I seeing a color change over a range? So this methyl violet here says from pH 0, that'd be 1 molar HCl, to about, I don't know, is that about 30 millimolar HCl. I see a gradation of color changes from yellow to blue. Why is that? Do you guys remember from our titration curves that we had shown for, what do we plot? Previously, where we showed molecules are changing as a function of pH and concentration? So we'll do this in a minute, but the moral of the story is that at the pKa, you have 50-50 mixture, okay, of protonated indicator and deprotonated indicator. But if you go 1 pH unit approximately above the pKa, so then you'll have about 90% deprotonated and 10% protonated. And that's sort of a little bit past your threshold where your eye can see, but somewhere around there, that's where your sensitivity is. So around 2 pH units, give or take. And now this pH range that's shown here is a little narrower, so from 1.2 to 2.8, that's about a 1.6 unit difference. So they're talking about plus or minus 0.8 pH units above and below the pKa, and that's where you can see that color range. So if you had this like yellow-blue indicator, you'd see green, and you'd see aquamarine, and you'd see that like lemongrass green. And you could potentially distinguish all those colors by eye, so that's the range that you'd be sensitive to. And that's because, like I said, over that narrow range of pHs, say 1.6 units, you can see color differences. So the best way of talking about that is to make a graph. And we've done this graph before, but a different way, but it's good to repeat this one. This is really important for understanding equilibria. So again, if you had a couple of axes. And on this side, you had the indicator concentration. And the units here don't matter for the purposes of this illustration. It could be micromolar or something like that. And probably every time I do this lecture, I'll change the units. But some lowish concentration that your eye can detect. And similarly, we have this sort of micromolar concentration. Say we have a micromolar total of dye. So the dye concentration is 1 micromolar, and that means that ind plus h ind is equal to 1 micromolar. That's a key constraint. And then you need to just decide, okay, well, h ind will be red. I don't know, did I do that right? Yeah, or orange. And deprotonated is yellow, let's say. Problem is that my yellow highlighter is kind of fat. So do that, make it. Hopefully, can people see that yellow up there? I don't know if I want to do that. Maybe make it bolder. I'm not sure what I got there. All right. So the ind is going to look like this. Remember that at high pH, or sorry, here's pH 5, 4, 3, 2, 1, 0. Something like that. 6, 7, 8, 10. Okay, so now we have our axes labeled. Somewhere around here is 50%. All right, so at extremely high pH, well above the pKa, back to the ind concentration will be high. Okay? And then right when you hit around pH 6, and remember it's 90% populated, and then right around pH 4, it's about 10% populated, and then that'll asymptotically come down to 0. So it's kind of hard to draw these curves, but those are the key points that you can always remember. At the pKa, it should be 50%. So you're right there, and here, I am at 90%, 90%, and 10%. Okay? When I'm 1 pH unit above, I'm there for the H end, and then when I'm 1 pH unit below, then I'm there. And then the protonated version does the opposite, right? And I'll pick that methyl orange color there. Sorry, not that you can tell the difference. So then it comes up, 10% there, 1 unit above the pKa, at 50% at the pKa, and then 10% at 1 pH unit below the pKa. It comes up asymptotically to 1. Okay? So again, 10% here, 90% here. And the magic point is here at the pKa. At the pKa, 50% is equal to ind, and 50% is equal to h ind. Okay, in this case, we're talking about 0.5 micromolar of each. Okay, all right. So that is why right over that near range, and that table I was giving you before, say plus or minus 0.8 units, is going to be right in this range, and that's where you'll have, if you were to look at this indicator dye as a function of pH, say from pH 5 up to pH 5.8 to pH 4.2. You'd see a real nice range of colors. Now, it's hard for me to do that, but you'd see really intense yellow up here, and then down here you'd see intense. And so as you went in between in this region, you'd see a mixture, okay? And it's hard, if you ever tried to mix crayons, okay, yeah, that's that's a success that I'm having there. This is not watercolor. So in any case, that's why, in that in-between range, you'll see a blending of the colors. And so you can get a pretty good explanation for why these indicators give you some latitude in calling the pH. So the question also is well, why is ind equal to h ind at the pKa why is ind equal to h ind when the pH is equal to the pKa? Well, you just remember your Henderson-Hasselbalch equation, and it's very straightforward. You can see mathematically that this pops out. So you just set this pKa or pH. It doesn't really matter how you solve this. And so you can just cancel these. You'll have 0 is equal to log And there's somebody who asked a question about 0 in logs after class, so I thought I would show that step for illustrative purposes. 10 to the 0th power, or 10 to the log will then equal ind over h ind, because that's the inverse function of log is raising something to raising 10 to that power. 10 to that is equal to 1, so then ind concentration is equal to concentration h ind. And of course, that's going to be the 50-50 point, because 100%, there's only one way that the two concentrations could be equal to each other, the total 100%, that's 50-50. Or you could say, well, half micromolar is the only way, there's only one concentration, half micromolar times 2, that equals 1 micromolar. All right, so good review and good explanation of acid-base indicators. And I'll get into some practicals towards the end about when to apply them. So in a titration experiment, what ultimately you have is some reagent that's either an acid or a base. And I mean, in an acid-base titration experiment, let's preface it that way. There are many titration experiments. You could do a redox titration experiment or any type of titration experiment. But in any case, in an acid-base titration experiment, you'll have either an acid or a base of unknown molarity, okay? Or there's an unknown number of moles in the solution. And what you want to know, what you would like to know is what its molarity is, or how many moles of that acid or base are dissolved in that solution. And so you're ultimately interested in not only the amount, but inherently also in the stoichiometry. And so you really do have to think carefully about your overall chemical reaction. So if I have something, like an unknown amount of sodium hydroxide, and I'm titrating into that unknown solution of sodium hydroxide HCl, I have nice one-to-one stoichiometry. And everyone knows that when you mix these two together, you're going to get water and sodium chloride. So this is a nice example of one-to-one stoichiometry. But that's not always the case. For example, you can have H2SO4. Does anybody know what that is? Sulfuric acid. It has 2 protons that are titratable, extremely acidic protons. So now the stoichiometry is off, and I need 2 equivalents. If you ever try to titrate sulfuric acid, you'll find you'll need more sodium hydroxide than you typically need to neutralize an equimolar amount of HCl. Okay, and that will make you sodium sulfate plus 2 water. Oh, sorry, that's not a nitrogen. Good call. Yes. So yeah, now you have, in this case, we'll call this 1-to-2 stoichiometry. So anyway, we'll get to this in a minute. We'll do a calculation where we have sort of a trickier stoichiometry, but it's not always the case that you're titrating a single proton. Okay, so in these acid-base titration experiments, or in any titration experiment, there's a series of there's a series of terms that are used, and they're not quite interchangeable. They mean slightly nuanced different things. And we talked about one special position in titration where the pH is equal to pKa, and that's where you sort of half titrated the species of interest. We half titrated methyl orange, for example. That's not this point here, which we're calling the equivalence point. That's not the equivalence point. That's half the equivalence point. The equivalence point is when you've fully exactly titrated that methyl orange. Okay, so that's the exact point that you have neutralized the acid or base you are titrating against. So you're going to add, some titrant here. This is a titrant. It's in your burette. Here's a stopcock. Bam. Here's your reaction. This is your titrant. And whatever you're titrating against, your reagent that you're titrating, your unknown, let's say, your unknown. Once you've fully titrated that unknown, that's when you've hit the equivalence point. Not just, not before, not after, right at the point. Okay, that's different. You might think that's the same thing, but that is not the titration endpoint. The titration endpoint is, it's almost the equivalence point. It's almost the equivalence point. If you're really good, you might just happen to hit it. But really what this is it's when the acid-base indicator, die becomes changes visibly to your visibly. Okay, so when you can visibly detect your acid-base indicator dye change, then you've hit the end point of your titration, and you have to pick the pKa of your acid-base indicator dye such that it will trigger very near to the equivalence point. But because of the fact that different indicator dyes are going to be slightly offset from the titration endpoint, then you're always going to be a little bit off in your titration endpoint from your equivalence point, and you just have to accept that as your experimental error. Okay, so that is a titration endpoint, and the titration endpoint ties closely into when the indicator dye changes. It's not quite the equivalence point, but if you're really good and you know how to pick the exact color of orange, dark orange, or yellow orange, then you'll be much closer to the equivalence point. All right, so an example calculation of just, like I said, just determining, say, the stoichiometry of a reaction. Let's say you're given 0.3 millimole of sulfuric acid. The question then is how many milliliters of, say, 0.5 molar sodium hydroxide are required to reach the equivalence point? I'm sorry, that equivalence is not legible. That's a Q, and that's a U. That's just not a good writing day. Okay, and so how many mils of sodium hydroxide